Everybody, Mr. Bowman here. Another video on 3.14 probability distributions. In this video, we're looking at some merit questions for the 2023 exam. And just a reminder, these are all past NZQA exam questions. I've just kind of compiled them all in one place for your convenience. So let's get into question number 15. And this here was all about a rare sheep breed in New Zealand, and it has origins from the Middle East. Blah, blah, blah. The wool fineness is measured in microns. So that's what the units on this axis are. It's about the microns of wool fineness. And then we've got the frequency of the distribution for the wool fineness of a sample of 49 of these sheep. The question asks us, use an appropriate distribution model, calculate an estimate for the probability of a wool fineness between 20 and 25 and 40 microns for each of the 4 sheep, and it specifically said to state the name and the parameter of the distribution that you're looking at. So I guess the first thing to note, wool fineness, it's probably going to be continuous data, because I imagine you can have part of a micron. So that means it's going to be one of the models that use continuous data. So that means it could be a normal distribution, it could be a uniform distribution, or it could be a triangular distribution. So looking at the shape of it, nothing normal about that. So let's cross out that. And we've now really got to think, does it look closer to a rectangle or does it look closer to a triangular distribution? And, I kind of maintain if you kind of do that, it looks pretty rectangular. This bit could have fitted here, this bit could go over here. So maybe it is rectangular in nature, the sample size of 40, but small, maybe you skewed it a little bit. And I think we can all agree it's definitely not triangular. So let's run with a uniform distribution here. So we're going to say it's a uniform distribution. Oh, I'm writing uniform, but uniform distribution. So when I'm writing that, the next part of the question, so if we look down that bottom sentence here, so it says state the name. So I've stated the name. I've now got to state the parameter. So the only real parameters of a normal distribution or a uniform distribution is the A value, which is the minimum, and the B value, which is the maximum. So A is equal to the minimum. And if you look at our graph, the minimum has a wool length of 20. And then B relates to the maximum potential microns of one of these sheep. The maximum in our case is down the very right-hand side there, that's 60. So those are your parameters. I've answered that last bit of the question. I now need to just discuss that, find the probability of a random thing for 4 sheep being between 25 and 40. So let's sketch our uniform distribution. So here's my uniform distribution over here. My minimum down the bottom there is going to be 20. I'm going to call that A. My maximum up here is my B value. So don't forget, these are just the parameters that I stated earlier on. And the question is asking me between 25 and 40. So let's kind of randomly draw on a line. So this line here can be the 25 and this line here can be to the 40. Definitely not to scale this diagram. So we've been asked to find the probability of that kind of shaded chunk there. So there are a few different ways to do uniform distributions. One of them includes calculating the height. But if you're finding a basic probability, there are other ways to go about it. So we're trying to find the probability that the wool fineness is kind of between 25 and 40 microns. So the way I do these questions is I use kind of my year 9 F over T type approach. T is the total width of the base of my uniform distribution. In this case, it's 40. So that's the difference between the 60 and the 20, width of 40. And then my F, my favorable outcomes, that relates to the width of the portion I'm trying to find the probability of, in which case the difference there is 15. So my probability here is 15 over 40, and I'm going to simplify that to 3 over 8, and I'll leave that as a simplified fraction. I'm not going to stress about that. So just to clarify, that's the probability of one of these sheep kind of having the microns between 25 and 50, but we've been asked about all 4 sheep. So the probability of all 4 sheep having that's going to be 3 to the power of 8, which is the probability of 1 sheep, and we're going to do that to the power of 4, and that's going to get us to 0.0198, and that there had a 4 dp rounding. I'm now on to question 16. I've left my working on there from the previous question, and I've basically been asked one of the assumptions I've needed for my calculations in the previous part. That was this 4 sheep stuff over here, is independence of events. Identify the appropriate event and justify this assumption in context. So I've got a little box here because I'm going to type away with my answer. I guess the starting point is, identify the event. That's the first thing the question's asked us for. So identify the event. And the second thing it's asked us for is to justify the assumption. So I always write down my bullet points to help me articulate my answer. So the previous question asked us to calculate the probability of 4 sheep having a wool fineness in between 25 and 40. So the specific event is wool fineness in relation to one of these actual sheep. So let's state that. So the event relates to one Asawi, forgive me if I've said that wrong, sheep having wool fineness. Fine, am I spelling that right? No, fineness of between 20 and 40, no, I'm saying that wrong again. So between 25 and 40 microns. So that's the event itself. So justifying that assumption, basically, do we think that's a good, so independence is what the question said the assumption was. Do we think assuming independence is a good assumption here? And I'm thinking no, because more likely than not, if you've got kind of a herd of sheep, a good portion of the sheep are going to be related to the other sheep, which probably means there's some kind of genetic element controlling or limiting the microns. So because a lot of the sheep will be related, a lot of the sheep as a result will have wool fineness of a similar micron. So that means they're not really independent, they're not really random. There's something else going on here. The genetic makeup of this, family of sheep are impacting the wool fineness. So I'm going to kind of state that here. So the assumption of independence, forgive my bad spelling, may not be a valid one. Like human, I'm going to here, being impacted by genetics, I imagine the fineness of a of wool from an Sawi sheep may also be impacted by genetics. I'm just kind of articulating what I talked about. So I talked about genetics doing it. I now want to try to link that to the group of sheep that I talked about, and the fact that there's something else happening. So it's depending on the family genetics, not randomness like independence assumes. So this means that a group of multiple sheep, because we are picking 4 sheep, remember, so we're probably picking them from a group of multiple sheep, may be related, and the wool fineness may be dependent on the family genetics rather than the randomness we would expect to see if the events were independent from each other. There we go. So hopefully that makes sense. So we've done some uniform distributions, and as always, I've started off my sentence with kind of what the question requires of me. And I always start off by talking about my assumption and then linking it to something from the real world that either matches or doesn't match the assumption that I'm dealing with. Okay, we are now on to question number 17. And we've got the rate at which a hen lays eggs can be modeled by a percent distribution. So we kind of know the distribution, which makes it a bit easier. And 99.3% of the time, she lays at least 1 egg a week. Calculate the average number of eggs that they lay. So this one we basically know straight away. So we've got the probability. We need to work backwards to find the average. This is going to be an inverse percent distribution question. So it's going to be inverse percent distribution. And I guess of big relevance is this inverse percent distribution question. They only work when x is equal to 0. So I need to find the probability that x is equal to 0. But the only issue is I don't have that. I've got the probability that but at least 1, so that's 1 or more, isn't it? So I've got the probability that x is 1 or more, and I know that to be equal to 0.9973, but I don't have x, the probability of x is being equal to 0. Luckily for us, when you've got this probability here, probability of at least 1, if you think of a number line, kind of like 0, 1, 2, 3, 4, 5, and then so on, because it could be anything above that, you've got this probability here, which means if you use the 1 minus p trick, you can then find the probability of it being equal to 0. So that's what I'm going to do here. So the probability that x is equal to 0 is going to be equal to 1 minus the probability that x is equal to or greater than 1. And we know that from above. So that's going to be 1 minus 0.9973. And then when I do that math, that gets me to 0. Oh, where's it gone? So that gets me to 0.027. So 0.0027. So we've now got that, and I know in an inverse distribution question that the probability of x is equal to 0 is equal to e to the power of negative lambda. So if I've got this, which I now do here, lambda is the only variable left in my equation, and I can use some algebra to find it. So 0.0027 is equal to e to the power of negative lambda. So this here is an algebraic equation, and I want to note e is just a number, so that means that lambda, that average, is the only variable left. I'm going to plug this into my graphics calculator, and I'm going to go straight to the answer. If you're not sure how to do that, do let me know, and I'm happy to reply with resources to help you out with that. But when I put that into the solver function, I got 5.9, and that they had a rounding of 1 decimal point. And I've got my lambda, so my average here, 5.9. So because these inverse inverse percent distribution questions are often merit questions, as they are here, because this is the merit video, merit always needs you to relate something back to context. So this here, what we've done here so far, is very mathy. So I just need to explain this answer in one sentence just to shore up that I've related my calculation back to some kind of context. So let's do that. So the estimated average number of eggs, oh gosh, not looking where I'm writing, the hen, or the hens lay each week is 5.9. So we're now on to question number 18, and this one's quite a weird one in terms of merit questions. I haven't seen one like this before, but so this question carries on from the egg stuff previously. What is the most likely number of eggs that the hen will lay each week? Justify your answer. So as we stated in the question, as the question stated, we know that this is a percent distribution question. And we previously calculated the lambda, or the average, to be 5.9 eggs per hen. So what I did for this question was using the percent point distribution as opposed to the percent cumulative distribution, so we'll cross that out. I just found the probability of each specifically. So what I did was I found, well, what's the probability that the hen lays exactly 0 eggs? And I put that in my calculator. If you don't know how to do that, let me know. I did 0.00247, and that there was 5 dp rounding. So I rounded all these to 5 dp. And then I just repeated the same. And then I was like, well, what's the probability of it laying exactly 1 egg? And that was 0.01616, same rounding. And then what's the probability of it laying 2 eggs? So same thing, still using PPD mode. So it was 0.04768. You can kind of see it's going up every time, so I haven't got my answer yet. So as soon as the answer goes down, I know I've hit my maximum, or my most likely outcome. So the probability that x is equal to 3, so I did that on my graphics calculator, and I got 0.09377, so roughly 19% for 3 eggs. And then we got the probability that x is equal to 4. That was 0.13831. So I'm still increasing. So I'm nearly at 14% now. So probability that x is equal to 5. That there was 0.16321. got x probability of exactly 6 eggs, 0.16049. And we can see here the probability is actually decreased for the first time. Ever so slightly, it's decreased. So based on that, that means the most likely number of eggs I'm going to get, assuming my percent distribution, is exactly 5 eggs. I'm now just going to write that down in a sentence. Because it is a merit question and this is all math, so I need to link it back to context for my merit mark. So the most likely number of eggs that the hen will lay each week will be 5 eggs. So there you go, and that wraps up this question. And now on to question number 19, and we've got some data on milk production for 200 dairy cows, and you kind of see it goes up, down, looks a bit normal distribution-y. For this herd, 10% of the dairy cows have produced or have production of less than 3,600 kilograms. Suggest suitable values for parameters of a normal distribution model that could be used. So the parameters of a normal distribution model are always going to be your mean and your standard deviation. So this time around, the mean, we could shorthand the mean by kind of just roughly guessing, well, in the middle of my data there, that's roughly going to be the mean, right? And this 5,250, that looks like it's going to be the mean in this particular case. The standard deviation, however, that's a lot more difficult to eyeball. You could use the plus or minus 3 standard deviation rule to help us that, but that's a bit guess and checky. So what we're going to do is I'm going to draw my normal distribution curve. So let's sketch this out first. So here's my curve. As we've said, we're estimating from the graph that the mean is going to be 5,250, and that looks like a pretty good estimate, to be honest. If we enter this data here, we know the bottom 10% have milk production of 3,600 or less. So that there is 3,600, and I know the shaded area here is going to be 0.1. So I actually quite like this because we don't have the standard deviation, which is a bit of a bummer. But drawing this data, doesn't this look like an inverse normal distribution question where you're asked to find the standard deviation? Yeah, it does look like it. So let's carry on with that. Let's keep the ball rolling. So I've now got to standardize my curve. Ignore that pen warning. I can't be bothered editing the video for that. But the mean is 0 and the standard deviation is 1 in a standardized normal distribution curve. We're dealing with a chunk of data that's down the bottom. That's 10%. And we're trying to figure out Z. We're trying to figure out how many standard deviations away from the mean this is. So this here is just an inverse normal distribution question calculator that you can put in your calculation, put into your calculator. So we're going to use inverse normal distribution on my calculator. The first thing to note, the tail is what the calculator is going to ask you to input, and that's a left tail, because you can see that's on the left-hand side of my graph. My area, that's the area you're trying to find or the area you're investigating. In this case, we're dealing with an area of 0.1 or 10%. We then always asked to put in the standard deviation, which we don't know this standard deviation. In a standardized curve, we know the standard deviation is always 1. And then finally, we always know the mean to be 0. And that's because the graphs need to be comparable. So when you plug that into your graphics calculator, you're going to get a Z value of negative 1.2816. So if you don't know how to plug that in and you need help figuring that out, let me know. I'm pretty sure I made a video about it and I can try to find that for you. So I've got my Z value. The next step is, so you've got your normal graph, you've got your standardized graph. You can now write down the Z formula. So Z is equal to X minus the mean divided by the standard deviation. So this here is just an algebraic equation. If you think about it, we know the Z, that's over here. We know the X value, that's the 3,600 from the question. And we know the mean, that was the 5,250 that we estimated. So the standard deviation is the only one we don't know. So this is an algebraic equation with one unknown. We can go ahead and figure that out. So So let's put everything in. So negative 1.2816, that's going to be equal to 3,600 minus 5,250, and all of that is divided by the standard deviation. If you're entering this into the solver mode of your calculator, which I encourage you to do, make sure there's brackets around the top there. If you don't know how to do that, again, let me know. And then your graphics calculator should spit out an answer of 1,287.5. And that there was run into 1dp. So we've now got the potential parameters of a normal distribution for this particular milk production for these cows. We know the mean, which we've estimated from the graph, and we've just calculated what a rough standard deviation would be. But because this is a merit question, this is still very mathy. We now just need to kind of communicate that in context to guarantee my merit mark. So the parameters suitable for a normal distribution for the milk production per season. So that last part's really important because that's the context of the question. So that milk production per season part, milk production per season would be, and let's just bullet point this. So we're going to have a mean of 500 or 5,250, and don't forget the units here are kilograms, and then we're going to have a standard deviation. And that was the number we just calculated of 1,287.5 kilograms. So quite a rough merit question, that one. That one was pretty tough, yet to be quite intuitive to kind of recognize, hey, this is just an inverse standard deviation question. Hopefully you found it useful. Now on to question number 20. And this one here, we've got a probability distribution of random variable n. So this might be random discrete variable type calculations. The number of kid goats, or goat kids, so that's baby goats, born per pregnancy of a particular dairy goat. So I'm assuming that means per pregnancy, getting 0 goats was a 10% chance, 1 goat was a 12% chance, and then so on for the rest of the graph. If you look at that probability of getting 2 goats, 3/4, that's quite a lot. The previous question, you would have been asked to calculate the mean and the standard deviation of the baby goats. And this question here, dairy farm goats preferred the dairy goat that produces an average of 2 goats per kid, so 2 goats per pregnancy. Comment on whether or not the data suggests that this type of dairy goats will be a good choice for a dairy goat farmer. There's a lot to unpack here, and I guess the first thing to note is, the first thing I probably want to talk about is this mean part here, because the mean is the average, and clearly the average is below 2. So that's probably the first thing I want to talk about, the mean. After that, I probably want to talk about the probability of there being 2 goats being exactly 0.75. So that's 3/4. So that's pretty good. If you're wanting if you're wanting 2 goats per birth, 3/4 of the time, that's pretty good. And then the final thing I want to talk about just the other probabilities. Why this group here, the 0-1 group, compares to the 0-3 group. So compare 0 and 1, 2, 3, and 4. So that looks like the rough structure that I want to follow. So the first thing about the mean, I'm just simply going to state that the mean number of baby goats is, 1.72. So the mean number of baby goats born per pregnancy from our calculations is 1.72, which is less than the desired average of 2. So that's the first thing to note. Oh, written number up here twice. Let's get rid of that. So the number of baby goats, or the mean number, wasn't it? There you go, the mean number. So that's obviously not ideal. Given you want an average, it's very clear that it's not enough based on the average. So from a positive note, so now I want to talk about this part here, because it is quite positive. If you're looking for an average of 2, the fact you get it 3/4 of the time is pretty good. The positive note from our data is that the farmer would get 2 baby goats per pregnancy 3/4 of the time. So that's pretty nice. The downside of it, so let's say they don't get 2 births. If you have a look here, this is 0.13, so 13%, and this is 0.3. So if you don't get 2 births, you're way more likely, also that's 0.22, isn't it? You're way more likely, about 7 times more likely actually, to get less than the average than more than the average. So not ideal. That's a bit of a downer, I think, and that maybe is the deal breaker. So if the farmer, or if the goat did not give birth to 2 baby goats, then the probability of getting 0 or 1, being 0.22, is roughly 7 times the probability of getting 3 or 4, being 0.03. So that's not good for your average. So that's why the average is lower, isn't it? This explains why the average, oh gosh, bad day typing, the average number of baby goats is 1.72, being below the desired average of 2. So based on this, we kind of need to wrap up to a bit of a conclusion. Do we think the farmer should get this particular goat? Probably not. It's quite far off. 1.72 is quite far off 2. There's no sugarcoating that. I don't think you should get the goat. So as a result, I do not think this type of dairy goat will be a good choice for the goat farmers. So that wraps up this question. It's actually the last question of the video too. I do hope you find them useful. And from that last question, hopefully you took out the idea of kind of scaffolding your answer. So stating what points you're going to talk about them before you actually get into that conversation. And again, I wrapped it up with a conclusion there, linking it back to the context and the choice of the goat farmer. But thanks so much for watching. Keep an eye out for the other probability distribution videos coming out. I've got a few merit ones and a few excellence to do over the next couple of weeks. And I really hope they benefit you and your exam.